And I'm live. I don't know. Now, I'll tell you, in terms of getting pulled over, in my first, I got my license when I was 17. And then I graduated college when I was 22. In the first 5 years of having a driver's license, I had 9 tickets in 4 states.
What are you doing? What are you doing?
Yeah.
You racing?
A little bit.
I drive fast.
So, but since then, since 2006, never gotten a ticket.
Oh, but he didn't give me a ticket though. I was like,
Yeah.
he was like,
It was until then, you know. Yeah. No, but I'll tell you, like a lot of them were my fault, but some of them definitely were not. For example, you know the summer crawl on 72. Okay. Summer crawl Saturday, driving, dropped a couple of friends off somewhere. I don't really remember where. And then I'm driving east on 72, and I'm trying to hit that jug handle circle to get on Route 9 going north. But like traffic was literally a snail's pace. So I saw a line of cars, and they were all for the circle. And I'm like, okay, I have 2 choices. I can either wait my turn, or I could be a jerk and drive to the front and just cut in. You know what I'm saying? So I decided not to be the jerk this time. You know, hold on. For me, I decided not to be the jerk this time, and I decided to wait my turn. But it turns out that all of those people were waiting their turn to get tickets for driving in the shoulder. Yeah, that was the first ticket I ever got. No, that was the second ticket I ever got. Because they were driving in the shoulder. And there was a cop there literally like a turnstile, like just like, hey, next guy up, you know, writing out tickets like you wouldn't believe. I know.
were you like, I wasn't riding?
No, I asked him, I'm just like, sir, is everything okay? Like, I had no idea, even to the point where he walked up. And he's like, license registration. I'm like, okay, sure, but can you tell me what's going on? And they're like, you're getting a ticket. I'm like, what? Oh, that was fun. I've heard about that. That can be a little bit of a myth.
No, I know. I was so lucky. He was so sweet. I was
Yeah.
like, my mom's on the way. I don't know. And he was like, you can go.
Well, I'll tell you one story and then we'll get started. So now I've been pulled over, but I haven't gotten a ticket since 2006. But one of the last times I got pulled over, and this is one of the benefits of knowing people in high school and being friendly with people and having these types of connections, even though, you know, they're not like close friendships. I got pulled over in Ocean Acres, and the cop was a guy I graduated with, you know? Yeah. And he's just like, and I had my wife and my kid in the back seat, right? And he's just like, he looks at the thing, he's like, oh, James Markey. I'm like, hey, what's up, man? He's just like, you remember me? I'm like, yeah, I remember, because I saw on his name badge, I saw his last name, so I knew who he was. But I didn't want to say it just in case he didn't know who I was, you know?
My friend's friend had like people in the car, and the cop didn't say anything about it. Like, let him go.
Oh, is that like a law thing? If you're under a certain age, you can't have a certain number of people in the car. Yeah. Oh, the other thing that you can do to get out of a ticket, screaming baby. Yeah, got pulled over one time several years back. My son was like 6 months old. And when we pulled over, we were like literally 2 minutes away from the house. But when we pulled over, like he was in the back seat just like flipping out. He's 6 months old. So the cop gets my information and he's just like looking at him in the back seat. And he's just like, because the sun was like right on his face, right? And the sun was on his face only because we were pulled over, you know? And he's just like, oh, can you, are you able to cover him from the sun? And my wife is like literally climbing over the back seat, trying to do this thing, whatever. And he felt awkward. So he's just like, yeah, just, you know, slow it down. I'm like, thanks. Kept going. So, ladies and gentlemen, here's the deal for today. As for today, oh, by the way, those of you in the chat, I see there's only 4 people in the chat, which is silly. Why are there only 4 people in the chat? There should be a lot more than that. Not you guys. Not blaming you. Blaming them. But leave your comment in the chat. That'd be fantastic for my attendance so I can update that. But as for today, we are going to be deep diving logarithms. I'm so excited. Logarithms, the musical tree. Nobody gets my jokes. Yeah. March, April. Anyway, back to this. By the way, being that we are done with February, I want you to think about this. We are 60% done with the school year.
Are you excited?
What?
Are you excited?
I'm excited for every day. Now, as for you, ladies and gentlemen, what you need to do is actually twofold. Number one, I would suggest that if you do have the worksheet, I gave out a worksheet either last class or the time before, I can't remember, but it says 7-2 practice on one side, and it says solving exponential equations with logarithms on the other side. I am going to be picking problems off of this at various times during the class period, but more importantly, if you do not already have them out, I'm going to need those notebooks out and open. Oh, I didn't? Okay, no worries. For those of you in the chat, I will, if I haven't already, and I'll double check this actually. No, I haven't. Okay, so I will do that. I will post the PDF of this worksheet into the chat in a few moments after I pass out this worksheet. You know, there's going to come a day next year, whether you are in high school or not in high school, but there's going to come a day where you're going to be like, man, I would give anything to hear Mr. Markey ask me to take my notebook out.
I don't know how to do that statement.
It's about 75% true.
I think it's pretty low.
Whatever. Let's see what we got here. So I just got to post it real quick, the PDF of this particular worksheet into that Google Classroom. Let's see what we got here. Add from the Google Drive. Let's see here. Come on. Load a bit faster. Or, you know, don't load a bit faster. Let's see. Ba-da-ba, ba-da-ba. There it is. 7.2 practice. And where is the other one? There it is. Solving exponentials. Insert both of them. PDFs for today. And they are now available through your Google Classroom stream. Excellent. Flip my screen over. Go back to here. Technology. I hate it so much, but that's what we're working with. Today is March 2nd, and I am calling this Solving Exponentials by Algebra and Logarithms. Now, this is going to directly relate to what we did in the previous couple of class periods. And yes, I know one of those previous class periods was you copying the notes that I provided for you. And I reminded you multiple times last class period to make sure that you had those notes copied down, obviously because they would play a role moving forward. But let's see what we got here. I'm going to be copying down a problem off of that worksheet 7-2. It is actually problem number 6, and I'm going to start with that one. The problem is 3 to the 6x minus 2 power equals 1 over 9 to the x plus 1 power. Now, last class, and again, this is number 6 off of that worksheet, just in case you can't see the details of this particular problem. There we go. So I'm looking at this problem, and I'm thinking to myself, okay, I got to solve for x. I got to get x by itself. I have multiple x's in the problem. Both of them are in the exponent. Oh, how do I go about doing this? Now, there are 2 ways, according to the title of this particular lesson, 2 ways of solving problems with variables in the exponent. One of them is the algebraic way, which I'm going to remind you of with this problem. Another is the logarithm way, which we are going to, as I said before, deep dive more today. The algebraic way is recognizing that there is a relationship between 3 and 1 over 9. More so, there is a relationship between 3 and 9. What is the relationship between 3 and 9 if you consider exponents? What is the relationship between 3 and 9 if you consider exponents? I'm hearing crickets. I don't know. Can you hear them? 3 definitely goes into 9. What about exponents? How do you turn 3 into 9 using exponents? Oh, she says, what is the lesson name? You say 3 times 3 or 3 squared. Yes. I'm moving that down because somebody in the chat asked for the title of the lesson, Solving Exponentials by Algebra and Logarithms. But yeah, 3 squared. 3 squared. We need to know 3 squared because in a moment we are going to convert that 9 into a 3 squared. Now, last time as well, and I'm gonna put this as a side note. And when I say side note, I'm literally gonna write it along the side and label it side note. Side note A to the negative n power equals 1 over A to the positive n power. This is a side note that goes back a ways for us. This is a side note that we need to know in order to handle this particular problem. The reason why is because of negative exponents. You have been taught in the past that when you see a negative exponent, it is best to get rid of the negative exponent by taking the reciprocal of the base. But in this instance, I actually need to take the reciprocal of 1 over 9. And if I take the reciprocal of 1 over 9, it's actually going to force that exponent to become negative. Let me write the next line of work, and I'm going to prove it to you. First of all, the left side is going to stay the same, but the right side is going to become this, and I'll move that up. There we go. Look what the heck happened. Look what the heck happened. First of all, the left side, nothing happened to it. The left side, nothing happened. Put it out of your mind for a moment. On the right side, the exponent x plus 1 didn't change. Put that out of your mind. But look at the parentheses. Look at what is inside of the parentheses. I changed that 1 over 9 into a base of 3. Now, I know, and I'll kind of write this out right here, actually, in orange. Here we go. I know that 1 over 9 is actually equal to 1 over 3 squared, because we just said that. 3 squared is 9. But according to this side note, I can rewrite this fraction according to what I have right here, and I can change it to be 3 to the negative 2 power. I need that for this problem. I need that 3 to the negative 2 power for this problem. Why? Because I need the bases to be the same. I need the bases on both sides of the problem to be exactly the same in order to move forward with this problem. If I can get the bases to be the same on both sides of the problem, then I can actually proceed with attempting to solve for the variable. Sorry, I was just looking at the comment. It was a comment from me, and I was just acknowledging that I read the comment. Before I actually set up what I need to do to solve this thing, I need to do one extra little thing right here. What? the heck did I just do? Say what now? I changed a couple numbers. But why? How? What? Who? First of all, yes, I did change something.
You distributed the -2.
Oh, say that word one more time.
You distributed the -2.
Yes. I distributed it. Yes. I distributed the -2, multiplied together the -2 and the x plus 1. Yes, 1,000 times yes. Because when you have power to a power, you have to multiply the two exponents together. And yes, you have to distribute that -2. So -2 distributed would become -2x and a -2, which is what I have here. From there, now I can do this extra little special case, this property that we wrote down, where I can set the two exponents equal to one another. Once I have the bases the same, and I have simplified the exponents, the property basically states that if the bases are the same, then I can set the exponents equal to one another. And now this is like an algebra 1 problem or a pre-algebra problem. I don't know. I didn't teach you algebra 1. I didn't teach you pre-algebra. I don't mean to bring them up and give you PTSD. I'm sure it does for some of you. But this is the problem that we have to solve. I'm going to add 2x to both sides. I'm going to add 2 to move it over to the right side. That cancels. This becomes an 8x. This cancels. And, oh, snap. What the heck do I get on the right side? Don't say nothing. 0. So people think nothing and they don't want to write anything, but 0 in this case, yes. 0 is a numerical value. Divide by 8, you get an answer of 0. All of that to show an answer of 0? Yeah, but that is the answer. By the way, you'll never be able to unsee what I'm about to tell you. You see where it says x equals 0? If you turn your head to the left, it looks like a smiley face with like X for hair. You'll never be able to unsee that. Just saying, that is my answer. Now I am going to prove that that answer is actually what it's supposed to be. In a moment, I'm going to prove it with my calculator. I'm just going to recap exactly what the heck we just did. If you look back at the original problem, you can't do anything until you get the bases to be the same. 3 squared is 9, yes, but also because it's 1 over 9, I'm going to have to flip it over like a reciprocal, which I did. 1 over 9 becomes 3, but as a result, the exponent turns negative, just like that side note said it would. I have to simplify a little bit by multiplying together the exponents. Once I multiply together the exponents, in this case by distribution, I can set the exponents equal to one another. That property basically stated if the bases are the same, then the exponents should be equal to one another, which I did down here. Solved it like an algebra 1 problem, and I got an answer of x equals 0. If you go to your calculators, which obviously, they're on your like Chromebooks and whatnot, I'm just going to kind of show you on my calculator real quick. Come on, calculator. There you go. Boop. If I plug a 0 into both of those exponents, it would be 6 times 0 minus 2, which I get that decimal. Doesn't matter what that decimal is. And if I do the other one, it would be 1 divided by 9 to the power of, 0 plus 1, which is just 1 clearly, which obviously is the same decimal. This is just checking my answer, and that proves beyond a shadow of a doubt that I do have the correct answer written down. This is the process that you could potentially go through for these problems. It's wonderful. Keep in mind one overbearing thought. I can only do this algebraic process if I can get the bases to be the same number. Let me repeat that. I can only go through this algebraic process if I can get the bases on both sides of the problem to be the same number. Give me a 2-digit number. 18? There you go. Is it possible to rewrite the number 18 so that the base is 3? The short answer is no, you can't. There's no way you can do it. Oh, Ms. Markey, 3 times 6. Yeah, I know 3 times 6, but the base is not 3. 3 times 6 is 18. The base is still 18. The only way you're going to be able to rewrite the base is if it was like 27. Because 27 is 3 cubed. Or 81. Because 81 is 3 to the 4th power. You can't rewrite 18 to look like that. You can't rewrite 18 to be 3 to some power. You can't. No, say it anyway. I see what you're saying. Now, the statement you just made is correct, but 3 to some power to be 18, right? Now, I want to take what you said and I want to expand upon it a little bit. 3 squared is 9, and 3 cubed is 27. Squared and cubed. The answer is somewhere between them. The answer for all of you is somewhere between 2 and 3. Where exactly? I don't know. I want you to write this statement down. There is an exponential. And when I say there, I mean like literally, look, right there. There is an exponential. I'm not telling a story. I'm just telling you a location. Right there. It's an exponential because you have a variable in the exponent. That's how you define what an exponential equation looks like. There's a variable in the exponent. Yay. We need to get rid of that 3. Because if we could get rid of that 3, we could get x by itself. Let me walk you through something real quick. I've talked about this in previous chapters. I want to give you a little bit of a demonstration and then a little bit of a verbal reminder. Okay, watch this. I'm going to demonstrate. Ready? Here we go. How do I invert what I just did? And I'm back where I started, right? That's called an inverse. That's an inverse operation. I take 2 steps forward. I invert it by taking 2 steps back. How do you get x by itself? Why subtract 3? I agree with you, but why subtract 3? Yeah, but why subtraction? I agree with you. That is the correct step. Why subtraction? It's the inverse operation. It's the inverse operation, which what will it do to this 3? It'll cancel it out, leaving you with the x. Hold on. How do you get the x by itself? You divide. Why division? of, exactly. This is multiplication. And in order to undo multiplication, you use the inverse operation, which is division, which will cancel out the 3 and get you the x by itself. Hold on. How do I get the x by itself? You would cube root it. Yes, because cube rooting and cubing are inverse operations. They will cancel each other out, allowing you to get the x by itself. I say all of that in preparation for this. There is an exponential. You can't subtract the 3. You can't divide by 3. You can't root out the 3. None of that will work. None of it. None of the regular operations that you have been taught in the past will get that 3 off of the exponential. The only way that you are going to get rid of that 3 is if you perform the inverse of an exponential. Now, you know addition, subtraction, they're inverses. You know multiplication, division, they're inverses. You know rooting and raising to a power, they are inverses. But the inverse of an exponential is a logarithm. A logarithm is the inverse operation. A lot of the time people want to be like, oh, Mr. Markey, what the heck actually is an inverse? I'm sorry, not an inverse. What exactly is a logarithm? How do you calculate a logarithm? Ladies and gentlemen, the best way of understanding what a logarithm actually is knowing that it is the inverse of an exponential. And I'm going to show you that by this. Look, first of all, whatever you do to one side of a problem, what have you always been taught? Yeah, you got to keep it balanced. I have no idea when you first learned that. 5th grade, 4th grade, kindergarten? I learned it in kindergarten. Look what I'm doing to the left side of the problem. Look what I'm doing to the left side of the problem. I am performing a logarithm that has a certain base on it, base 3. And I am going to do the same thing to the right side of the problem. Because as you just said, whatever you do to one side, you have to do to the other. You have to keep it balanced. The reason why I bring up all of this logarithm stuff is because this is the only way that we are going to solve this problem. The only way you are going to solve this exponential is with a logarithm. Now, I just told you that a logarithm is the inverse operation. If 2 inverse operations come into contact, what is supposed to happen? When 2 inverse operations come into contact with each other, what is supposed to happen to them? Adding 3, subtract 3. Multiply by 3, divide by 3. They should cancel each other out, leaving you with the variable. Now I'm going to write this in red with a red pen so you can see a little bit better. This logarithm right now is programmed to be base 3. That logarithm of base 3 and this exponential of base 3 cancel each other out, leaving you with just the x. X equals log base 3 of 18. Now, we're not done yet, but I just want you to pause on this moment and reflect on what the heck this just did and how this will help us moving forward. Because I'm going to show you a word problem after this, a word problem that is going to exemplify what the heck it is you are supposed to do with this stuff. Ms. Markey, what is log base 3 of 18? Put that aside for a moment. Don't worry about that. Answer me this. Did we get x by itself? That's all that matters. We will calculate what log base 3 of 18 is in a little bit. We will. And I will give you the exact numerical value of it. But you should be recognizing the fact that this gets you x by itself. That is what's important. Give me that. There we go. So let's see what we got here. There are multiple ways of calculating this. I am going to show you a few different ways right now of getting the exact value. You have the benefit of having this calculator. This calculator, you have that benefit. Anything that has a TI-84 or better can do what I'm about to show you. Check this out. Math. You hit math and you go down to option A. Look at that. Log base. If you hit that, it gives you the option of typing in the exact numbers that you need. The base of 3 and the insides of 18. Huzzah! There is our answer. I'm going to write that answer down, but I'm going to do approximately. X is approximately 2.631. I'm going to round it to 3 decimals. 2.631. Log base 3 of 18. Again, that's under, I'm going to write the directions down for that, but that's under math. And option A is something called log base. I need you to understand something. TI-83 calculators, your phone calculators, they do have log, but they don't have that option. They don't have that option. So that's what I wrote down. I wrote down this as a numerical value for my answer. Mr. Markey, that decimal looks pretty messed up. I know, it does. Let's check our answer. Let's see if it actually works. 3 to the power of 2.630929754. Huzzah! There is a little bit of rounding error because your calculator can only go to so many digits. But that is the answer. That is indeed the answer. Pretty sure the calculator rounded it up. Hold on. Second, enter. Change that 3 to a 4. Yep, just under 2. Yeah, that's about 18 as well. I love problems like this. Okay. Couple of things here. Flip. I need you to write down this information. In a TI-84 calculator, this only works for a TI-84, which you do have on your Chromebooks. You would hit math, the math button, and then you would select option A, which is log base. That's if you have a TI-84 calculator. Now, not everyone has a TI-84 calculator. I mean, you guys do, obviously, on your Chromebooks. But if you don't, then for everything else, you need the following formula. And when I say the following formula, ladies and gentlemen, you need the following formula. This is a just-in-case situation. And when I say just in case, I mean like you can use TI-83. You can use a scientific calculator. You can use your phones. And the following formula will work. I'm going to show it to you on my phone in a little bit. But it's basically this. This is called the change of base formula. This is called the change of base formula. This marker's dead to me. Yeah. That was a terrible throw. I'll show you how it works. I'm going to bring up my TI-83. If you need to calculate log base 3 of 18, you have a log button on your calculator. It's been staring you in the face this entire time. Look at it right there. Log. However, every single log has a different base. The base that we need is 3. We need a base of 3. Unfortunately, this button is not set to base 3. This button is set to base 10. And you can't change it. You can't. This button, you cannot reprogram it. This button, you cannot change. It is base 10. Here is the reminder that it is base 10 right there. Base of 10. So, I can use the following change of base formula that we just wrote down and type in the following. I could do log of 18 divided by log of 3. Close the parentheses around the top, of course, and that'll give me the exact decimal that I am looking for. Let me show you my phone. I showed you my phone last time. Something like this. Check this out. There's my phone right there. Zooming out, zooming out. There's my phone. Mr. Markey, I don't see a log anywhere. I don't see a log anywhere. Ha, ha, ha. I guess you don't have log on your phone. No, it's there. Look right there. It's right there. Log. You could type in log of 18, close parentheses, divided by log of 3. There it is right there. You see that decimal? That decimal number. It is exactly what I am looking for. You don't need a fancy calculator to do log. You have it right there. Did I tell you guys about Wabbit Emu? No? If you have an Android phone, there you go. If you have an Android phone, then you can download the following app, Wabbit Emu. Check it out. It's basically an emulation of a TI calculator. I downloaded the TI-84 Plus skin. Wabbit Emu with a W. The emu stands for emulator or emulation. Anyway, back to this. Just making sure I get the live chat back up here so I can actually see it. Okay. I have a word problem for you. I have given you advice on buying cars. Let's talk about one of those things that you could do with a car. People buy cars, they take care of them, and eventually they want to upgrade. I want you to write this down. I purchase a car for $10,000. The average rate of depreciation is 15% per year. And this marker is also dying on me. Do I have a better one? Pretty certain I do. Haha, I don't like that. Let me see how good this one is. That's pretty good. I'll use that one for now. Yeah. I missed. Anyway. How long until the car reaches a value of $2,500. I purchase a car for $10,000. The average rate of depreciation is 15% per year. How long until the car reaches a value of $2,500? Cars tend to lose money over time. You drive them from point A to point B, you use them, you upkeep them, you put in as much gas as you can when you can. It doesn't matter. The car is going to lose value over time unless it turns into a classic or it's involved in a murder investigation. Doesn't matter. What? Was that involved in a murder investigation? All right. You know what appreciates in value over time? You know what actually gains value over time more often than not? Houses. You say money? Money actually loses value over time. We talked about that. Inflation. Anyway, the buying power, But to this, I purchased a car for 10 grand. The average rate of depreciation is 15% per year. How long until the car reaches a value of 2,500? Now, I have written down in the past for you, and I'm going to write it down again right here, a formula for calculating such a word problem with a rate of depreciation. It's y equals a parentheses 1 minus r parentheses to the x power. We've written that down in the past. I want you to write that down again. Now, the question is how long? The question is time. How much time will go by? How long until the car reaches a value of $2,500? What variable in this equation represents time? Yeah. Oh, snap. We need to solve for x. We need to solve for an exponent. We're going to need a logarithm. You can guess and check, but they need a bit of accuracy, Well, we are going to do that, but ultimately you can't guess and check what x is. Watch what happens. 2,500 equals 10,000 parentheses 1 minus 0.15 to the x power. First of all, I put in 10,000 into the spot for A because A is the initial value. $2,500 is the resulting value. 15% is the rate. So I left it as 0.15 because that's what I needed to do for this problem. The x power, the x exponent, that is time. That is what I need to solve for. This is what I'm saying. You can't plug and chug numbers here. You can't just start plugging in numbers and hope that it works out perfectly because it's not going to work out perfectly. I could be like, okay, 10,000 parentheses 1 minus 0.15 to the second power. Nope. To the third power. Nope. To the fifth power. Nope. To the eighth power. Nope. To the ninth power. Well, look, in between the 8 and 9, it went down. Well, I need more accuracy than that. I need it to at least 2 or 3 decimal places. Guessing and checking is going to take a while. So instead, I'm going to set this up so that we can solve using a logarithm. First of all, the first step that I am actually going to do is divide both sides by 10,000. I'm going to divide both sides by 10,000. Because that's 10,000 times the result, I'm dividing by 10,000 to peel it off of the problem. I also simplified the parentheses. 1 minus 0.15 became 0.85. Now it is time for the logarithm step. Now it is time to peel off that 0.85 so that I can get x by itself. I peel off that 0.85 by utilizing a logarithm. But notice, and I'm going to say this and zoom in on it so you can see it a little bit easier. What base did I put on that logarithm? Why 0.85? I couldn't hear you. Not just because it's the rate of change. The rate of change was 15%, by the way. It is 0.85. But the reason has nothing to do with the rate or anything like that. The 0.85 has everything to do with the fact that it is the base on the problem. It is the base underneath the variable. Because it is the base that we are trying to remove from the problem in order to get x by itself, it should be the base on the logarithm that you use to solve the problem. Look what happens on the right side. On the right side of the problem, log base 0.85 and a base of 0.85 cancel each other out, leaving you with the variable of x. That is a huge key right there. Then I'm going to get x equal to this calculation. X equals, well, log of 0.85 parentheses 0.25. Ugh, if only I knew what that answer was. Well, I'm going to go to my calculator and get it. Let's see what happens. Flip. Math. A, which is log base 0.85, 0.25. There's my answer. X is approximately 8.53. Wait a minute, it was a word problem. Word problems need more than just that. Let me zoom out a little bit. 8.53 what? 8.53 what? I need a unit on there. You told me that x was time. 8.53 what? Why? That's the exact reason. It is years. Absolutely, it is years. And the exact reason why you need to put years as the unit is because the rate was measured per year. The rate and the time unit of x need to be the same. They need to be the same. If this were measured per hour, then it would be hours. If this was measured per minute, this would be minutes. It depends on what the rate is measured in. A lot of the time, they'll tell you like, oh, 15% annually. Well, that's per year. Weekly, monthly. We'll talk about what that means moving forward, obviously, with the different problems that we have. I love it. Eventually, this is building up to a project. Eventually. This is going to build up to a project in which you will have the opportunity to research banks and cars and houses. It's going to be great. It's going to be phenomenal. Of course, you all have to do different cars and different houses. I do have a system for that. Split my page here. I want to show you just the key difference between exponential form and log form. They are saying the exact same thing. They are saying the exact same thing. They are. They absolutely are. When you have y equals b to the x power, it is the exact same mathematical rationale as this logarithm form. the base on the exponential is the same base that is on the logarithm. Logarithm form allows you to get the exponent by itself. And the resulting value of y is what is inside of that logarithm. They mean exactly the same thing. For example, what is 10 cubed? What is 10 cubed? You can do that in your head. Huh? Yeah, cubed. Yes. Who? You said 300. You're multiplying them. It's 1,000. Check this out. 1,000 equals 10 cubed. That is a true statement. Now let me rewrite it in logarithm form. If I rewrite it in logarithm form, it would be log base 10 of 1,000 equals 3. I'm going to show you that on the calculator in a moment. But these two statements are saying the exact same thing. They are just written in different forms. If you see log base 10 of 1,000, what it's really asking you is 10 to what power will give you 1,000? And of course, the answer is 3. If you go to the calculator, chita, and you just use that regular log button, it doesn't have the base on there because that regular log button is base 10. You can do that. You can do log of 100, which is clearly 2. Log of 10 is 1. Answer me this. Answer me this. Check this out. Log of 1. What the heck? Log of 1 is 0. Well, what does that mean? Well, if log of 1 is 0, that means log base 10 of 1 is equal to 0. Convert it to exponential form. 10 to the 0 power equals 1. That's what it's really saying. That is how I need you to recognize how logarithms work with one another. They are inverses of one another. They are basically saying the same thing from two different sides of the same coin. It's wonderful. Love this thing so much. Logarithms are going to be the bread and butter of this entire chapter. Again, you're going to be researching cars. You're going to be researching houses. It's going to be wonderful. You're going to be figuring out rates of growth, how long it takes for a certain object to reach a certain value, things of that nature. We're going to get into those details. To wrap up today, I want you to write down one problem. And this is actually from the back of that worksheet. I want you to write down one problem from the back of that worksheet. It's problem number 11. And this is what we're going to wrap up with today. This problem is an exponential problem. How do you know that? There's a variable in the exponent. I need to get the variable n by itself, but there are several things preventing me from doing so. I have to get rid of that 10. I have to get rid of that 9. I have to get rid of that 3. Which one do we take care of first? I have to get rid of the 10, the 9, and the 3. Which one do you peel off first? Ooh. Think SADMEP. You got to take PEMDAS backwards. If you're going to guess, you got a 1 in 3 shot. It's the 3. You got to take off that 3 first. It's subtraction in order to cancel out addition. So I'm going to subtract 3. I'm going to get 9 to the n plus 10 power equals 78. Here's a hidden trick for you. Here's a hidden trick for you. You see this exponent right here. Something that you probably should get in the habit of doing is putting that exponent in a little set of parentheses. Which one, the 9 or the 10, do we take off next? It's actually the 9. You know why? Think sad mep. Sad mep. Sad mep. Sad mep. Parentheses go last. Parentheses go last. You got to leave that n plus 10 for last. Technically, exponentials fall under exponents. Miss Markey, the n plus 10 is an exponent. I know, but there are parentheses around it. And because there are parentheses around it, you can't touch that 10 yet. You can't touch that 10 yet. So I'm going to convert it. I'm going to convert this thing into logarithm form. And if I convert this thing to logarithm form, it would be log base 9 of 78 equals the exponent n plus 10. Logarithms allow you to get the exponent by itself. I hear packing up, and I'm not done with this problem yet. I'm going to go to my calculator and get log base 9 of 78. Log base 9 of 78 gives me this decimal, 1.983. Again, you can do that by hitting math and hitting that option for log base. Now that I am finally within those parentheses, I can subtract 10. My answer should actually be this decimal, negative 8.017. We will pick up with more of this, ladies and gentlemen, on Thursday. Oh, I'm going to leave that up there for a moment, obviously, because people in the chat may still want to leave their comment or have that copied down. As I said, we will have more practice with this on Thursday.